In this video, I'll be walking through my notes on Level 2 Mechanics. A link to the PDF and a list of corrections is in the video description. Scalars and vectors. Vectors are quantities with size and direction. Scalars only have size. Here are a few examples. Scalars include pressure, temperature. For example, you can't be warm in a particular direction. Time, though this one is debatable at higher levels. Mass, you can't be massive in a direction. And energy does not have direction. Vectors, on the other hand, include displacement, where if you're displaced from A to B, that involves both a distance as well as a direction. You can have a velocity in a direction, an acceleration in a direction, we can apply a force in a direction, and we can also apply a torque in a direction, for example, clockwise or counterclockwise. Distance versus displacement. Distance describes the length of the path an object has travelled. Displacement describes the difference between the object's start and finish points. Distance and displacement are only the same if the object has travelled along a straight path. So for example, an object moving along a straight path will have the same distance and displacement, whereas an object moving along a curved path might travel along this line here. However, its overall displacement is a lot shorter. Speed. Speed describes how quickly an object's position changes. The vector of speed is velocity. Its scientific units are meters per second, which we can write as meters divided by seconds, or if you accept that 1 over a second is second to the power of -1, we can also write ms minus 1. We can describe speed with the equation that our speed, symbolized by v, is distance divided by time. Note that our units of meters and seconds give us our final unit of meters per second. Using this equation in an example, how long does it take for a car moving at 10 meters per second to travel 25 meters? Using the equation, velocity is distance over time, which we can rearrange for t, substitute in our distance and velocity, which gives us 2.5 seconds. Acceleration. Acceleration describes how quickly an object's speed changes. Its scientific units are meters per second, which we can write as meters per second, or if you accept that we can write this as meters per second squared, and that 1 over second squared is second to the power of -2, we can also write this as ms minus 2. We describe acceleration with the equation acceleration is speed over time. When an object accelerates against its velocity, we say that it decelerates. For example, if we have a car traveling in a particular direction, if our acceleration was to act in the opposite direction, this would reduce the size of our velocity, and we would say that the car is decelerating. Using this equation in an example, a car accelerates from rest at 5 meters per second for 7 seconds. Calculate its new speed. Using the equation acceleration is velocity over time, rearranging it for velocity, and putting in our acceleration and our time, we get 35 meters per second. Distance-time graphs. The slope of a distance-time graph is the velocity. The steeper the slope, the higher the velocity. So if we have a distance-time graph, if we have a flat line, that means we have no slope. No slope means no velocity. So in this case, our object would be stationary. If we have a straight line, that means that our slope is constant, and therefore our velocity is constant. However, if the line is curved, that means that the slope is changing, which means that the velocity is changing, and so we have acceleration. In this case, the slope is increasing, indicating an increasing velocity, which we would call positive acceleration, whereas if we had a line more like this, our slope is decreasing, and therefore we would have deceleration. Giving an example with numbers, keeping in mind that slope is velocity, we could have a constant velocity of 5 meters per second, and then our line gets steeper, indicating a higher velocity of 15 meters per second. Our line then goes flat, indicating we have no velocity, the object is now stationary, and then we get a velocity in the opposite direction, indicating that our velocity is negative. Speed-time graphs. The slope of a speed-time graph is the acceleration. The area is the distance. The steeper the slope, the higher the acceleration. For example, drawing a velocity-time graph, a flat line means our slope is 0, meaning we have no acceleration and a constant velocity. If we have a straight line, that means we have a constant slope and therefore a constant acceleration. A curved line on this graph would indicate changing acceleration, which we don't assess at this level. Putting numbers to our graph, we could have a constant slope and therefore a constant acceleration of 4, which then decreases to 2, and then a flat slope indicating 0 acceleration or constant velocity, followed by a negative slope or negative acceleration. If we were to calculate the area underneath this line, we will have calculated the distance, for example 55 meters. Practically what this would mean would be to calculate the area of this triangle, this rectangle, this triangle here, this rectangle here, and this last triangle, and then adding all those together. Kinematic equations. Kinematic equations are used to describe objects with constant acceleration, including 0. They contain a mix of the following values: initial velocity, symbolized by vi, final velocity, symbolized by vf, distance, symbolized by d, acceleration, symbolized by a, and time, symbolized by t. The first kinematic equation equals the final velocity by taking some initial velocity and adding on an increase in velocity for an object accelerating in a given time. For each of the equations I'll be mentioning, they will have all of our stated values here, with the exception of one. This first equation here is missing distance. The reason I point this out is this can often be a useful tool in figuring out which equation to use. Our second equation is solved for distance and starts with vi times time, which gives the distance the object would have travelled if its velocity remained vi, and then adds on a second term, which gives the increased distance travelled if the object is accelerating over a given time. This equation here is missing the term final velocity. Our next equation, vf squared equals vi squared plus 2ad, is missing the time. And our final equation, d equals vf plus vi over 2t, where this term here is the average velocity. So essentially what this is a rearranged version of v_av equals distance over time. This equation is missing the term acceleration. And now just to point out, what happens if the acceleration is equal to 0? For our first equation, if a is equal to 0, then this term disappears, and we just get that the final velocity is equal to the initial velocity, which is what we'd expect since the velocity isn't changing. Making the acceleration 0 for our second equation causes this term here to disappear, which gives us d equals vit, which is a rearranged version of our v equals d over t, an equation you'll already be familiar with for cases with no acceleration. For our third equation, if the acceleration is 0, this term disappears, and then if we square root both sides, we can cancel out this power, and we get vf equals vi, which is the same equation we ended up with here. Let's now walk through an example. A car accelerates from 5 meters per second to 8 meters per second in 10 seconds. What distance did it travel in this time? We're given our initial velocity is 5 meters per second, our final velocity is 8, we have a time of 10 seconds, and we're trying to determine the distance. The one value we don't have and don't care to find is the acceleration. This is a clue to use the one kinematic equation that doesn't have acceleration, which is this one here. Substituting in our numbers, we get 65 meters. For another example, a boulder rolls off a cliff and falls 20 meters to the ground. Calculate the duration of its fall. Our distance is 20 meters, and because it's downwards, we'll make that negative. Our acceleration is the acceleration due to gravity, which is 9.8 meters per second, and because it's also downwards, it's also negative. Our initial velocity is 0, and we're trying to determine the time. The one value we don't have and we don't care to find is our final velocity, cluing us into using the one equation without the final velocity, which is this one here. Our task now is to solve this for time. First of all, we can recognize that vi is 0, which means that this term here disappears. We can now multiply both sides by 2, divide both sides by the acceleration, and then square root both sides and swap them around, giving us our solved equation, which we just need to add in our numbers to, which gives us 2.0 seconds. Drawing vectors. Vectors have two properties. Magnitude, which is indicated by length. For example, we can have 20 newtons, which then if we were to write 60 newtons, we would draw an arrow 3 times as long, and so on. Vectors also have direction, which is indicated by orientation. There are a number of ways this can be described, such as simply saying left, or giving it as an angle. We could also say east, or we could say down. In summary, anything that is communicating a specific direction. Scaling vectors. To scale a vector, meaning to affect its size, we multiply it by a scalar. For example, if we have this vector here, v, to half the size of this vector, we could just write 0.5v. To double its size, we could write 2v, and for 1.5 its size, we could write 1.5v. Multiplying a vector by a negative causes it to point in the opposite direction. So negative v is going to be the same as v but in the opposite direction, and as well as multiplying it by a negative to make it point in the opposite direction, we can scale it at the same time. Equating vectors. Similar to scalars, vectors form equations. To do this, we can use these techniques. Circles are zeros, meaning that vectors forming closed paths equal 0. For example, if we had the vector a plus b plus c plus d, these all form a closed path, meaning that the path returns on itself, and so the sum of these vectors is 0. Similarly, we could write a plus b plus c, once again forming a closed path, and so once again the sum of these vectors is 0. This works no matter how many vectors you choose, so a plus b plus c plus d, once again all sum to 0. The second technique is equivalent paths, meaning that vectors or sets of vectors that start and finish in the same place are equal, so that a plus b starts and finishes in the same location as c, meaning that a plus b equals c. Similarly, a plus b gets you to the same place as c plus d, and so a plus b is equal to c plus d, and finally a plus b plus c gets you to the same place as d, and so a plus b plus c is equal to d. To be clear, this only works when we consider these as vectors with direction. Trigonometry refresher. In this course, you're going to be doing a lot of trigonometry. For this reason, it will be assumed that you know the basics of Pythagoras and SOHCAHTOA. For this reason, it's worthy of a recap. If we have a right-angled triangle, the longest side is what we call the hypotenuse, and if this is defined as our angle, then the side opposite is called our opposite side, and the side adjacent to it is our adjacent side. If we were to instead define this as our angle, then the opposite and the adjacent would be the other way around. Pythagoras tells us that the hypotenuse squared is equal to the opposite squared plus the adjacent squared, which we can rearrange for each side. The term SOHCAHTOA is a method of remembering trigonometric ratios. SO tells us that sine of the angle is equal to the opposite side divided by the hypotenuse. Ka tells us that the cosine of the angle is equal to the adjacent over the hypotenuse, and TOA tells us that tan of the angle is opposite over adjacent. Vector components. It is often useful to separate a vector into horizontal and vertical components. Knowing the total magnitude and the angle, we can use SOHCAHTOA. So if we have our vector here, pointing at a known angle, we can separate it into our horizontal and vertical components. If we note that this is our hypotenuse, this is our adjacent, and this is our opposite, for v horizontal, we can use that cosine of the angle is equal to our v horizontal divided by our hypotenuse v. Multiplying both sides by v gives us this equation here. We can do the same for our vertical using the SO relationship, which is that sine of the angle is equal to the opposite, our v vertical, divided by our hypotenuse v. Once again, multiplying both sides by v gives us this equation here. Relative velocity. Velocity is always relative to something. No velocity is truer than another, which is to say we generally define velocities on Earth as relative to the surface of the planet, since its motion is relatively predictable. However, that's just a decision for convenience, and this relative velocity is no truer than if we'd defined the velocity as relative to the clouds moving above. The relative velocity between two objects depends on whether they're in the same direction or opposing. Same direction velocities subtract. For example, if we have a car traveling at 5 meters per second relative to the ground, being followed by a car traveling at 7 meters per second relative to the ground, their velocity relative to each other is 2 meters per second. If, for example, the cars were traveling at the same velocity, for example 5 meters per second, then their relative velocity would be 0, and they would be stationary relative to each other. On the other hand, opposing velocities add. So if we had the same cars traveling at the same speed but in opposite directions, these velocities would add, giving us 12 meters per second relative to each other. Here we see a truck moving at a particular velocity, carrying a cannon, which fires a ball with an equal and opposite velocity to the truck. These two velocities cancel out, and the ball is momentarily stationary before falling to the ground.
Look at that. Fantastic. I mean, look, it doesn't move at all. It's going straight down.
Gravity. Earth's gravity accelerates all objects downwards at 9.8 meters per second, whether that be a feather or whether that be a hammer. This means an object's velocity would increase by 9.8 meters per second, independent of the object's mass. If an object experiences air resistance, however, its total acceleration will depend on its mass, which is why down here in Earth's atmosphere, the acceleration of a feather will be much less than the acceleration of a hammer. Here we see a bowling ball and feathers released to fall at the same time. As you might expect, the bowling ball falls faster, due to the friction with the air having a much greater effect on the feathers. Pumping out the air and repeating the experiment, we see the ball and the feathers accelerate identically, proving that gravity accelerates all objects at the same rate. In this simulation, I've positioned balls of helium, glass, rubber and stone above the ground. Upon release, we see the glass, rubber and stone fall at different rates. This happens because the force from the air friction affects them in proportion to their different masses. Because our ball of helium is less dense than the air around it, the buoyancy force exceeds its force of gravity. As a result, it accelerates upwards. Repeating the experiment but removing the air, without the force of buoyancy and the force of air friction, all four materials accelerate downwards at the same rate. Projectile motion. An object in projectile motion has both horizontal and vertical motion. For example, if we have a tennis ball here, with an initial vertical and horizontal velocity, for simplicity, we assume that there is no air resistance. The only force acting in flight is gravity, and that gravity is uniform and downward, meaning that gravity never changes and it always points down. This means that for our horizontal motion, there is no acceleration, since the gravitational acceleration is purely in the vertical direction, meaning that the horizontal velocity will not change, giving us a constant horizontal velocity, which we can just describe with v equals d over t. For vertical motion, however, the acceleration due to gravity is 9.8 meters per second downwards, which causes our vertical velocity to constantly change, initially decreasing until at its maximum height it reaches 0, after which it starts to increase in the opposite direction. Because we have acceleration, we need to use our kinematic equations. Now, it's important to emphasize that although our velocity is changing, our acceleration does not. It is always 9.8 and it is always pointing downwards. Let's now go through an example. A football is kicked and travels at a velocity of 30 meters per second at an angle of 40 degrees to the horizontal. Calculate the maximum height it reaches. For this, we need to consider the vertical motion. We can find our initial vertical velocity using our sine relationship, where our vertical component of this 30 is the opposite side and our 30 is the hypotenuse. That means that sine of our angle 40 is equal to the opposite that we're trying to find, our vertical initial velocity, divided by our hypotenuse of 30. Multiplying both sides by 30 gives us VI equals 30 sine 40, which gives us 19 meters per second. At the maximum height, we know that the final vertical velocity is going to be 0, and so we have our initial velocity, our final velocity. We know that the acceleration is due to gravity and is going to be negative 9.8 meters per second, and we're trying to find our distance. The only quantity we don't have and don't care to find is our time, so we can choose the only kinematic equation without time. Solving this for d by subtracting vi squared from both sides, and then dividing both sides by 2a, putting in our numbers, gives us 18 meters. I have here a ramp from which I'll be rolling a ball bearing at a range of velocities. Stitching this footage together, we can see that regardless of the horizontal velocity, the ball takes the same amount of time to fall, demonstrating that we can analyze the horizontal and vertical motion separately, as ignoring air resistance, one does not affect the other. This model, put together by the European Space Agency, visualizes the relative strengths of gravity across the surface of the Earth. Blue regions are low, red and yellow are high. The deviations observed are caused by a number of known and potentially unknown factors, including the difference in composition of the Earth. It's important to understand that when we give a value for the acceleration due to gravity, such as 9.81 meters per second, this value is very much an estimate. Force. A force is an influence that acts to accelerate objects. It is measured in newtons, symbolized by a capital N. Isaac Newton came up with 3 laws that give an insight into the relationship between force and motion. Newton's first law states that an object will only change its motion, or in other words, its velocity, if a force acts upon it. For example, if we were to kick a ball, the ball goes from stationary to moving only because we've applied a force to it. The reason the ball eventually stops moving is because the force of friction acts upon it, changing its motion once again from moving to stationary. In summary, any time the velocity of the ball changes, it is due to a force acting upon it. Newton's second law states that when a force acts upon an object, it will accelerate proportional to its mass, so that when we apply a force to an object, that object is going to accelerate at a rate depending on its mass. For the same amount of force, an increase in mass is going to see a decrease in acceleration. Newton's third law says that forces exist in equal and opposite pairs. For example, if we had a brick on a table, the brick is going to apply a force downwards to the table, and in response, the table is going to exert an equal and opposite force onto the brick. We also see this with gravity, where the Earth applies a force onto the Moon, and the Moon applies an equal and opposite force onto the Earth. I have here an RC helicopter, and 3 things I'd like you to try to explain. How does it go up and down? How does it go back and forwards? And how does it rotate? Here's some footage of it flying to help you think. Now for the explanations. To move up and down, the helicopter spins its main rotor, which is shaped to apply a downwards force to the air. In return, the air applies an equal and opposite force to the rotors. If this force is greater than the force of gravity, the net force will be upwards, and the helicopter will accelerate up. If the force is equal, there will be no net force, and the helicopter will remain at the same altitude. If the force is less than the force of gravity, the net force will be downwards, and the helicopter will accelerate downwards. To move forwards and back, the helicopter spins its back rotor. If the rotor forces air upwards, it will experience a downwards force, which will tilt the helicopter backwards, giving our main rotor force a backwards component, which will accelerate our helicopter backwards. If the back rotor blows air downwards, it will experience a force upwards, tilting the helicopter forwards, giving the force on the main rotors a forwards component, and accelerating the helicopter forwards. The helicopter is able to rotate using its two main rotors. These spin in opposite directions, and if they spin at equal velocities, they will apply equal and opposite torques to the helicopter. In this case, the torques cancel out and there's no net torque on the helicopter, but if one of these rotors is slowed, the torques will no longer equal, and the helicopter will experience a net torque, causing it to rotate. Here we see two Finnish astronauts sitting on top of a car that is accelerating towards a concrete barrier. The car is stopped as it experiences a force from the barrier. Since our astronauts do not experience this force, and objects in motion will remain in motion unless acted upon by a force, they continue with their original forwards motion. I have here a zero-gravity air floater, a name that makes for good marketing, but not good physics. What's really going on, as you've probably deduced, is that a flow of air upwards, producing an upwards force on the ball, is counteracting the downwards force of gravity, which we can regard as more or less constant, and certainly at no point zero. You might wonder, why does the ball stay within the column of air, even when it moves back and forth? This happens because our moving column of air is at a lower pressure than the surrounding stationary air. This is due to Bernoulli's principle, which is not assessed within this course. The surrounding high pressure regions produce a restoring force on the ball, directing it more or less towards the center. Here we see a valiant hero leading the charge to free a stranded pickup truck. Performing a vector analysis, we see the man applying 3 forwards forces on the truck. However, these are only made possible by an equal and opposite force backwards. The net force applied to our truck by our valiant hero is therefore 0, and our man's efforts are unfortunately in vain. Hooke's law. We can describe the force produced when a material is deformed as the force is equal to some constant called the stiffness, or alternatively the spring constant, multiplied by the displacement from equilibrium. The negative sign indicates that F and X are opposed. For example, if we had a spring with a block attached to it, if we were to displace the block in this direction, the block is going to produce a force in the opposite direction. And so when you are using this equation, let's say you want to solve this for k. This equation, rearranged for k, is negative the force divided by x. If we had a force of 20 and a displacement of 10, putting those values in is going to get us negative 2. Now importantly, stiffness is not negative. The mistake we've made is that either f or x need to be negative because they're in opposite directions. And so making either of these negative, for example at 20, is going to cancel out with this negative and give us positive 2. Stiffness describes the newtons of force a material exerts for every meter of displacement. So if we had a stiffness of 5 newtons per meter, that means we get 5 newtons of force for every meter of displacement. We can plot the relationship between f and x on a graph, in which case the slope of the graph is the stiffness k. Initially, as we increase the displacement, we're going to see an increase in force. Our trend is going to be roughly linear, indicating a constant slope, and therefore a constant k. This is called elastic deformation, and following elastic deformation, the material returns to its original shape. However, if we were to increase the force beyond the limits of our material, we would start to see plastic deformation. Following plastic deformation, the material is permanently deformed. For this reason, we see the slope and therefore the stiffness of the material changing, up until we reach the point at which the material breaks. Let's now use this in an example. A 2 kg mass is suspended from a spring, causing it to extend 0.3 meters. Calculate the stiffness of the spring. We're given our mass as 2 kilograms and our displacement as 0.3 meters. To find the stiffness, we need to find the force. We know that the force is gravitational and can therefore be found as mass times gravity. Our mass is 2 and our acceleration due to gravity is negative 9.8, which gives us negative 20 newtons. Using Hooke's law, F equals negative kx, we can rearrange for k and then substitute in our numbers, where because the force is negative, our negatives cancel out, giving us 67 newtons per meter. I have here a 100 gram mass attached to a spring. Increasing the weight in 0.5 newton increments, we get an extension of 5, 10, 15, and 20 centimeters. The gradient of this graph gives the stiffness K, the amount of force for each meter of extension. Circular motion. Objects in circular motion are described using the following terms. The radius is half the circle width. The diameter is the circle width, which is twice the radius. The circumference is the length of one lap, where a revolution is a complete lap. The term period, symbolized by capital T, is the amount of seconds per revolution, so the amount of seconds for our object to go around once. On the other hand, our frequency is the revolutions per second. As this language suggests, these two are what we call mathematical reciprocals, meaning that frequency is 1 over period and period is 1 over frequency. We can furthermore write the velocity of our object as distance over time, specifically the distance of one lap divided by the time taken to complete one lap. Centripetal acceleration. As an object changes direction, its velocity changes, even if the size of the velocity does not. This is called centripetal acceleration. A force or combination of forces providing centripetal acceleration are called centripetal forces. Centripetal literally means center-seeking, which tells us that the centripetal acceleration always points towards the center, whereas the velocity points tangential, which is 90 degrees to this acceleration. Now, it's important to note that the centripetal force is not a force on its own, it is a role that other forces provide. So if I were to ask you what are the forces acting on the Earth as it goes around the Sun, the answer is only gravity, which provides the centripetal force. If you were to swing a ball around on a rope, the centripetal force is provided by the tension, and if you had a car going around a flat circular track, the centripetal force is being provided by the friction between the tires and the track. So in summary, the centripetal force is not a force itself, it is a role that other forces play. We can write the centripetal force mathematically as the mass times the centripetal acceleration. This is also equal to mv squared over r. And so if you wanted to find the centripetal acceleration, you could take this equation here and divide both sides by mass and find that the centripetal acceleration is just v squared over r. Let's now go through an example. A 1500 kilogram car drives in a circle of 20 meter radius on flat ground. It completes a lap every 60 seconds. Calculate the minimum friction force the tyres must provide. Our mass is 1500 kilograms, our radius is 20, and our period is 60 seconds. To find our friction force is playing the role of our centripetal force, so we can describe it with our centripetal force equation, where we have the mass and the radius, but we don't have the velocity, so we need to find it. To do this, we can take distance over time, or in other words, circumference over period. Circumference is 2 pi r, and period is t. Putting in our numbers gives us 2.1 meters per second. Using this in our equation below gives us 330 newtons. I have here a 50-gram disc resting on a turntable. Setting the turntable to spin, at a certain speed the disc slides off. This occurs when the centripetal force required to keep the disc moving with the table exceeds what the friction force can provide. This maximum force should be the same regardless of where the disc is placed. By observing the rotational period at which the disc slides off, we can calculate its approximate value. Starting with the equation Fc equals mass times velocity squared over radius, we know the mass and radius but not the velocity. We know velocity is distance over time, which we can write as the distance of one rotation, aka the circumference, divided by the time for one rotation, aka the period. The equation for circumference is 2 pi r. Substituting this in and simplifying, we get that the centripetal force is 4 pi squared mr over t squared. Placing the disc at a radius of 10 centimeters, the disc slides off at a rotational period of 0.0105 seconds. Putting these numbers in gives us a force of 1790 newtons. Repeating this for a radius of 3 centimeters, the disc slides off at a rotational period of 0.0053 seconds, which gives a force of 1757 newtons. As expected, the forces are more or less the same, with a difference of only 1.8%. Torque. As described earlier, a force is an influence that acts to accelerate an object. Similarly, for the context of rotation, a torque is an influence that acts to angularly accelerate an object. It has units of Newton meters. If we were to apply a force on a wrench at a particular distance from the pivot, the resulting torque is given by the equation force times distance, where the symbol for torque is the Greek letter tau, not to be confused for the letter T. Let's now go through an example. Two 3.0 kilogram kakapo sit on a horizontal branch. One 0.2 meters from the trunk, the other 0.3 meters. What is the combined torque they produce? We have the mass of each bird and also their radiuses. The gravitational force the birds produce is equal to their mass times the acceleration due to gravity, which is 3 times 9.8, giving us 29 newtons. The torque of our first kakapo is its force times its radius. Putting in those numbers gives us 5.8 newton meters. Doing the same for our second kakapo gives us 8.7 newton meters. Our total torque is those torques added together, which gives us 15 newton meters. Equilibrium. Objects in mechanical equilibrium experience no change in their motion, be that linear or rotational. For this to occur, the net force and net torque must equal 0. We can write this with fancy mathematics as the sum of all the forces is equal to 0 and the sum of all the torques is equal to 0, where these symbols here just mean the sum of all things. In the exam, if you're asked to state the conditions for equilibrium, either of these answers is fine. Note that an object in equilibrium need not be at rest. What I mean by that is that an object could very well have a non-zero velocity while having a net force and net torque of 0. For systems with multiple pivots, such as a bridge on 2 supports, any pivot can be chosen for analysis. Note that because torques at r equals 0 are 0, they will zero out of equations. What I mean by that is that we recall that torque is equal to force times radius. If we were to choose our pivot to be here, and wanted to determine the amount of torque provided by the force from this support, because its r is equal to 0, that is that its distance to our pivot is 0, since they're at the same location, this would make r 0 in this equation, which will make the torque 0. This could be used to our advantage if we were, for example, wanting to find the torque produced by this support, but we had no information about this support. The equation we would make by choosing our pivot here would not contain the term for this support, and so we could essentially ignore it. Let's now use this in an example. A 1500 kilogram car is parked on a 3000 kilogram bridge. Calculate the force provided by support A, and on our diagram we have that the supports are 10 meters apart and that the car is 8 meters from support B. The first thing that we can recognize is that the bridge must be in equilibrium, meaning that the torques are balanced. So we can state that the clockwise torque is equal to the counterclockwise torque. If we were to draw a diagram with our forces, we have the force upwards from support A, the downwards force from the car's weight, the downwards force from the weight of the bridge, and an upwards force from our support B. However, because we're wanting to find the force provided by support A, if we made our pivot at A, then because its r would be equal to 0, it would disappear out of our equation. We instead should make our support B our pivot, particularly because this means we can ignore any information about it. And so we already know that the supports are 10 meters apart, and we know that the car is 8 meters from support B, and given that the supports are 10 meters apart, that means the middle of the bridge must be 5 meters from support B. Next, we need to identify what the clockwise and counterclockwise torques are. With our pivot at support B, support A is acting to turn our bridge clockwise, and our two gravitational forces are acting to turn the bridge counterclockwise. So our only clockwise torque is that from support A, and the torque from our car and the weight of the bridge make up our counterclockwise torques. Knowing that torque is equal to force times distance, we can substitute in the distances multiplied by the forces, where our gravitational forces can be written as the respective masses times gravity. Now to solve for Fa, which is what we're trying to find, we just need to divide both sides by 10. Putting our numbers in, we get 26,460 newtons, or 26,000 newtons to two significant figures. I have here a mass on a wooden ruler resting on two supports, with digital scales displaying measurements for mass, which we can multiply by the gravitational acceleration 9.8 to find the forces. A mass is initially positioned so that the support force is equal. If the mass is moved to the left, however, we see an increase in the left support force and a decrease in the right. We can explain this by first recognizing that because the system is in equilibrium, the net torque about any point must be 0. And with this in mind, consider the torques acting about the mass. The clockwise torque, which is provided by the left support, must equal the counterclockwise torque provided by the right, ignoring the mass of the ruler for simplicity. Torque is equal to force times distance, because the distance to the left support is less than the distance to the right. For the torques to remain equal, in the same proportion, the force from the left support must be greater than the force from the right. Center of mass. Center of mass describes the average position of a set of objects, weighted by their masses. Now, this might not make a lot of sense initially, so what I'll now try to do is break that down in a more intuitive way. In a more practical sense, two objects on a pivot will balance at their center of mass. The center of mass of two identical objects is halfway between them, meaning that if we were balancing two identical Earths, their center of mass and the location a pivot would need to be for them to balance is halfway between. However, if we replaced one of our Earths with Jupiter, the mass of Jupiter is much larger than Earth's. The center of mass is therefore much closer. I have here a glass, two forks, and a matchstick. Balancing these just right, and spending an embarrassing amount of time doing it, we see what initially appears to be counterintuitive. All the weight is on the end of the matchstick, so why doesn't the matchstick topple? If we consider where the match is pivoting and draw a line through it, what we see is that we have a roughly equal amount of mass on either side of our line, meaning that our match fork structure has its center of mass above this pivot, and since their combined force of gravity acts from this point, it has a distance of 0. As the distance to our pivot is 0, no torque is produced. Energy. Energy describes the potential for an object to change its motion. Its units are joules, symbolized by a capital J. Energy comes in many forms. In this course, we will be considering the following. Kinetic energy is the energy of motion and is given by half mv squared. Gravitational potential energy is energy stored against gravity and is given by mgh. And finally, elastic potential energy is energy stored against elasticity and is given by half kx squared. Conservation of energy. Energy is never created or destroyed, only transferred into different forms. This idea is called conservation of energy and is one of the most important ideas in all of physics. For example, if we had 10 joules of electrical energy and we were to power a lamp, we might have 3 of those joules transformed into light and 7 joules into heat. The main takeaway is that this energy wasn't destroyed and these energies weren't created. This electrical energy was just transferred into different forms. For another example, we could have a ball with 35 joules of gravitational potential energy, and upon falling we could have 2 of those joules lost to air resistance and 33 transferred to kinetic energy. Finally, if we had a wood log with 100 joules of chemical energy, upon being burned, we might have 10 joules of that used as light and 90 joules as heat. Let's now go through an example. A tuatara falls 2 meters from a tree. Calculate its velocity just before it lands. The only information we're given is that we have a height of 2 meters. Now we can assume that the kinetic energy that the tuatara gains is equal to the gravitational potential energy it had before it fell. We know kinetic energy is half mv squared and gravitational potential is mgh. We can divide both sides by mass, effectively cancelling it out, giving us half v squared equals gh, getting rid of the half by multiplying both sides by 2, and then square rooting both sides, putting in our numbers, giving us 6.3 meters per second. Work. When energy has been used, we say that work has been performed. Work is essentially another term for energy, and so unsurprisingly, it has the same units of joules. When a force is performed over a distance, the work performed is given by force times distance. For example, if we were to apply a force to a mass on a spring over a particular distance. And now, just as an aside, let's apply that to an object falling from a particular height. In this case, the force is the gravitational force, which we know is given by mg, which means knowing that work is equal to force times distance, and knowing that the force is mg, and we can write the distance as the height, what we end up with is the equation for gravitational potential energy. Let's use this in an example. A 95 kilogram dirt bike is rolled up a ramp onto a 0.80 meter trailer. Calculate the work done against gravity. We know the mass is 95 kilograms, and we know the distance. We know that work is equal to force times distance, and although we have the distance, we don't have the force. However, we do know that the force is gravitational, so it must be equal to mass times gravity. Putting in those numbers, we get 930 newtons. Using that in our equation below gives us 740 joules. And now, just to be clear, it doesn't matter whether we lifted the dirt bike directly or took it up a longer path, the distance moved against gravity is the same in both cases, even if the total distance moved is not. Power. Power is the rate of energy consumption. It is measured in joules per second, which are commonly called watts, symbolized by capital W. As an equation, we can write that power is energy used over time. For example, a 25 watt stereo consumes 25 joules per second. Since our 25 joules divided by 1 second is equal to 25. Just the same, a 10 watt fan consumes 10 joules per second. Momentum. Momentum is a measurement of motion that takes into account both mass and velocity. It has units of kilogram meters per second. As an equation, momentum symbolized by lowercase p is equal to mass times velocity. And so, as we can see, momentum takes into account mass and velocity in equal proportion. And although kilogram meters per second is quite a mouthful and might seem hard to remember, just bear in mind it's just the units of mass multiplied by the units of velocity. A bee and a car might travel at the same velocity, but have very different momentums due to their considerable mass difference. For example, a bumblebee and car traveling at 10 meters per second will, because of their very different masses, have very different momentums. Rebounding ball. What is the change in momentum of a rebounding ball? Consider a ball with an initial momentum of 5 towards the right, rebounding off a wall, causing it to rebound with the same momentum but in the opposite direction. To find the change in momentum, it's important to understand that the momentum undergoes two changes. The first change is to cancel the initial momentum. So we initially have a momentum of 5 towards the right. To cancel this out to 0, the momentum needs to change by 5 in the opposite direction. The next change in momentum is to provide the final momentum. Having cancelled out the initial momentum, we now need to take our ball from 0 momentum to a momentum of 5 in this direction. To do that, our momentum simply needs to change by 5 in this direction. The total change in momentum is therefore these changes added together, which gives us a total change in momentum of 10 towards the left. Impulse. The longer a collision takes, the smaller the force. This concept is described by the following equation. Force is the change in momentum divided by the duration over which it changed. Impulse itself as a quantity is defined as the change in an object's momentum. So if you're asked to find the impulse, you're being asked to find the change in momentum. To understand this concept further, we can plot force and time on graphs. Consider driving in a car with a certain velocity. If you were to slam on the brakes, you will experience a large amount of force over a short duration. However, if you were to slowly brake, the force you'd experience would be smaller, but it would be spread over a longer duration. Because in both cases, we went from having the same amount of momentum to a momentum of 0, the momentum change is the same in both cases. Graphically, this change in momentum is represented by the area underneath this graph. Let's now use this in an example. A 0.050 kilogram tennis ball traveling at 6.2 meters per second rebounds off a wall and now travels at 5.9 meters per second in the opposite direction. The ball is in contact with the wall for 0.0045 seconds. Calculate the average force on the ball. We know the mass of the ball. We know the initial and final velocities. Important to note that because they are in the opposite direction, one of them needs to be positive and one of them needs to be negative. Which one doesn't matter. The only thing this will affect is whether your answer is positive or negative. I'll talk more on this after we've done the calculation. The last thing we know is the duration of the collision. To find the force, we need to use the equation of the change in momentum over time. We know the time, but we don't know the change in momentum. To find that, we need to take the final momentum and subtract the initial momentum. This is how you find the change in any quantity. Knowing that momentum is mass times velocity, we can make that substitution. Putting in our numbers gives us 0.61 kilogram meters per second. Now back to the question of making velocities negative. The way I set this question up was that our 5.9 was positive and our negative 6.2 was negative. The fact that we've got a positive change in momentum out means that it's pointing in our positive direction, which we've defined up here as this direction. So the direction of our change in momentum is the same. Now, if we had instead made this one positive and this one negative, our 6.2 would be positive down here, and our 5.9 would be negative, and if you pop that into your calculator, you'll still get 0.61, except it'll be negative. And because we have swapped the direction of positive and negative, the fact that our change in momentum is negative means it points in the negative direction, this direction here, exactly the same as before. Now, knowing our change in momentum and our duration, we can substitute these into our force equation, giving us 135 newtons. Conservation of momentum. The total momentum of a set of objects will only change if an external force acts upon them. This is called conservation of momentum. For example, if before we have an orange ball with a momentum of 20 towards the right and a green ball with a momentum of 30 towards the left, if we define this direction as our positive direction and add these momentums together, that gives us positive 20 plus negative 30, which gives us negative 10. If these two balls were to collide, we might see that afterwards, the orange ball has a momentum of 25 towards the left, and the green ball a momentum of 15 towards the right. Once again, adding these momentums together, once again gives us negative 10. Our total momentum before and after is the same, and so momentum is conserved. Using this in a couple of examples, billiard balls experience gravity and the support force. Though they are external, they are also balanced. The net external force is therefore zero, and momentum is conserved. However, a ball in flight experiences an unbalanced external force due to gravity, and so consequently momentum is not conserved. And so to summarize, momentum can still be conserved if there is an external force, if that external force is balanced such that the net external force is zero, like it is here and like it isn't here. What is an external force? Consider a falling apple. As it falls, its momentum increases. We could say that momentum isn't conserved because gravity is an external force. An external force is a force applied by an object whose momentum we've ignored, often because it's impractical or impossible to measure. In the case of the apple, we've ignored the equal and opposite momentum the apple's gravity has imparted to the Earth. And so to summarize, even though it looks like our apple has gained momentum in such a way that momentum is not conserved, in reality, just as the Earth has attracted the apple has attracted the Earth. As a result, the Earth gains an equal and opposite upwards momentum, such that these momentums cancel out, and momentum is actually conserved. However, considering that momentum is mass times velocity, because the mass of the Earth is much larger than the apple, its resulting upwards velocity is much smaller. So small that it's impossible to measure, and it's easy just to call gravity an external force and say that momentum isn't conserved. Long story short, momentum appears to not be conserved only when a part of the system is ignored. Here we see a man mixing Mentos and Coke to manufacture a rocket. The reaction expels gas and fluid out the bottom. Via conservation of momentum, the downwards momentum that the fluid leaves with provides the bottle with an equal and opposite upwards momentum. As simple as this may be, the physics behind this is the same physics that gets us to the moon.